Alright, welcome to the Exponential Units Review for Algebra 1. We'll start with number 1. We have this table and we have to decide which ones are explicit and which ones are recursive. So if we remember right from class, explicit was given in the form of it looked like a linear function or an exponential function, and if it was recursive, that's the way we thought about it in our head, which was you take the previous term and you multiply it by something or add something to it. So if we look at the first one, f1 is 10, so we're given the first term, and then we're given some function where f of n is equal to f of n minus 1, so that's the previous term times 4. That's going to be a recursive rule. The second one, f of n equals 5 times 3 to the n minus 1. That's going to be explicit because we're only given a rule, not what the first term is. The third one, again, that's back to recursive because I can see I need to know the previous term to get the next one. That's recursive. And finally, f of n is equal to 10n plus 2. That's going to be explicit once again. Number 2, use the geometric sequence. 10, 30, 90, 270, 870. Write the following. Write a function to represent the sequence above. So geometric sequence is going to be in the form of a sub n is equal to a1 times r to the n minus 1 power. So if we look at this, a sub n is equal to a1, our first term is 10, times r is what we're multiplying by to get from term to term, which it looks like it's times 3. So it's 3 to the n minus 1 power. To find the 11th term, well, I'm just going to take my value, 10 times 3 to the 10 minus 1. I'm going to go to my calculator. So it's 10 times 3 to the 11 minus 1, and I get 590490. 590490 is the value of my 11th term. Number 3, Jack is reviewing the change in the value of an investment. It says time in years, it goes from 0 to 5 to 10 to 15 to 20. So there's not adding by 1. And then investment in hundreds of dollars, he's got 0.25, so it's $25. $50, $100, $200, $400. So it says write a function Jack can use to model the data. Well, it's either going to be linear or it's going to be exponential. So when I look at this, easiest thing to do, like we talked about in class, is go to my calculator. I'm going to make a new document. I'm going to do a list, and I'm going to type in my x values. And we had 0, 5, 10, 15, and I forget what that last one was. I don't really want to go back to it, so we're going to go to 20. And we'll go over to our y values, and we label it. And then we're going to plug in our 0.25. Point 5, 1, 2, and 4. And then if we graph that, so we're going to make a new page, list and spreadsheet, like we've done. Sorry, not list and spreadsheet. New page, data and statistics. We pick our variables, and we look at that. That does not look linear. That for sure looks exponential. And it says write a function. Well, I'm going to analyze regression, exponential, and there's my function. 0.25 times 1.15 to the x. So f of x is equal to 0.25 times 1.15 to the x power. That's exponential. Why is this type of function a good model for these data? And it's a good fit because the data is not increasing by a constant rate. If it was increasing by a constant rate, we'd see something linear like adding a half, adding a half, adding a half, and so on. Okay. Number 4, the population of a sample of bacteria triples every minute. If A is the initial population, Kim believes the population 3t to the A can be used to find the population after t minutes. Explain why Kim is correct or incorrect. Well, Kim is going to be incorrect because the function for something tripling, that's exponential. And that's always going to be the form of A times B to the x. And we know that A is the initial, B is the rate, which in our case the rate is times 3 because it's tripling. So your explanation of why she's incorrect is because she has the variables in the wrong spots. And then for the second part, if it's incorrect, what is the correct equation? Well, the correct equation is going to be y equals our initial value, which A is the initial, times B, which is our rate, which is 3 to the t power in this case. Number 5. Thomas began an exercise program to get back in shape. He plans to jog 10 minutes on the first day and increases his jogging time by an additional 2 minutes each day. Write an explicit rule modeling the number of minutes he will jog on the nth day. So this is arithmetic. And we know it's arithmetic because he's not multiplying with something, he's adding 2 minutes each day. So the rule for arithmetic is f of x is equal to the first day. So he starts with 10, and he's going to add 2 minutes for each day after that first day. So plus 2 times x minus 1, because he doesn't have to add anything for that second day. So if we simplify that, f of x is equal to 10 plus 2x minus 2, which becomes 2x plus 8 is his equation for how much he jogs each day. So even if we plug in like any day after the first, most like the first day he plugs in 2 times 1, which is 2, plus 8 is 10, so that's his 10 minutes. And then the second day we know should be 12, 2 times 2 is 4, 4 plus 8 gives us 12. Part B, write a recursive rule. Well, the recursive rule is even easier because it's f of x. If we go back to up here, we're looking for something that looks like this. So we need f of x and f of 1. Well, f of 1 is 10 because that's how much you jogged the first day. So it's going to be 10 plus, not 10 plus, because it's not 10. We don't know what we're starting with. It's f of x minus 1, so it's the previous term plus 2 extra minutes. So if we know the first term is 10, then the second day is 2. 10 plus 2, which is 12. Number 6, how would the graph of y equals negative f of x be shifted if it was changed to 5 to the x plus 2? So we started with negative 5 to the x, and we shifted it to positive 5 to the x plus 2. So it's going to do two things. So we lost the negative sign. So when we lose the negative sign, or add the negative sign, the graph is going to be reflected over the x-axis. And the second thing is we get this added 2 to the end of it, which is going to shift up 2 units. Number 7, the graph below represents 3 to the x. State the domain in the range. Well, we know that domain is the inputs. And we can see that x goes left forever. And x also, because that arrow, x is also going to go right forever. So our domain is negative infinity to infinity. And then my range is the possible outputs. Well, my outputs stop at 0 and they go up forever. So my range is 0 to infinity. Part B, sketch the graph of negative 3 to the x. Well, we just said on the last problem that this negative just reflects the graph over the x-axis. So all these points that I can see, like this point, and that point, are going to be reflected down below the x-axis. So I have a point at 0, -1, 1, -3, because I was at 1, +3, and then my last point is at 2, it was at 2 +9, so it's at 2, -9, and then my graph is going to go like that. So now it's reflected. How does the graph of g shift compared to f of x? Well, reflected over x axis. And we also could have used our graphing calculator to graph that function to make sure. How did the domain and the range change? Well, the domain is still -infinity to infinity. That doesn't change. The range, though, now it has a lowest point, and then it stops at 0. So it goes from -infinity to 0. Part C, sketch the graph of 3x plus 2. Well, I know that 3 to the x looks like this. There's 3 to the x. But then it's this plus 2, so the whole thing is just shifted up 2 units. So I'm going to take all these points that I know and just move them up 2 units. So that 1, that 0, 1 here is now at 0, 3. The 1, 3 point is now at 1, 6. And the 2, 9 point is now at 2, 11, 12, like that. And then that horizontal axis that I used to have, that was at 0, that's now at +2. So my graph is going to look like that. How does the graph shift? Well, shift it up 2 units. How does the domain and the range change? Well, guess what? Domain is still -infinity to infinity. The range now, instead of it going from 0 to infinity like on the original, it now goes from 2 to infinity on the new one, because it now has, it starts at 2, goes up forever. All right, number 8, use the table to justify 3 to the 1/2 x is an exponential function. Well, I'm just going to plug this in. I'm going to plug in these x values into my function, get some outputs. So if I plug in a 0, I get 3. You can use the calculator for this. Or we can also look at, this is an exponential, so that's my initial value right here. This is my ratio, so I'm multiplying by 1/2. So half of 3 is 1.5. Half of 1.5 is 0.75. Half of 0.75 is 0.375. And my common ratio each time is 1/2. And my justification is that we have a common ratio of 1/2 for each term. Alright, number 9, use the table below. How does the function represented in the table change over equal intervals? Well, first thing I look at, all my x's change the same. They're all changing by 1. And my y's, well, it's not linear. But if I look at a calculator, I've got 64 divided by 256 is 1/4, or 16 divided by 64 is 1/4, or 4 divided by 16 is 1/4. So it looks like for equal intervals changing by 1 in the independent variable, the corresponding dependent value changed by -1/4. That's not true. They didn't change by -1/4. They changed by a factor of +1/4. So the answer is going to be B. Turns out that for whatever reason, this is just a typo, that D is also the correct answer because it was the same value. Part B, based on that change, what type of function is it? Well, since it has a common ratio, it is exponential. All right. Number 10, use the graphs shown below. Prove each function is either linear or exponential. Well, this graph is kind of in a bad spot, but so the one that clearly looks exponential is f of x. Which function is exponential? That's going to be f of x. So that means g of x has to be linear. Prove your answer. Well, my proof of my answer is if I take these points, So 0, 1, 1, 3, and 2, 9. We have a common ratio of 9 divided by 3 is 3, 3 divided by 1 is 3. We have a common ratio of 3, and also that function can be written as has a starting value of 1 and a ratio of 3, so y equals 1 times 3 to the x. G of x, same thing, except this time we know it's linear, and I see some points. I've got a point at -2, 3, a point at 0, 2, and another point down here at 2, 1. Well, I can find the slope as a constant slope of what looks like my slope is I go down 1, right 2, down 1, right 2. So I have a slope of -1/2. And another justification could be that that function is written as y equals -1/2 x plus my y-intercept, which is at 2. 11. Geneva received a gift card for $25 to Cold Stone Creamery. Each ice cream cost the same amount, so the relationship between the amount of money left on her card and the total amount of ice cream can be represented by a linear function. After several weeks of purchasing ice cream, Geneva went online to see the amount of money left on her card. She noticed that one row in the table did not make sense. Which pair of values in the table is incorrect? So if it's linear, then all of my changes should be constant based on my outputs or my inputs. So if I look, these first two, 22.5 minus 17.5 divided by 3 minus 1. So I've got 22.5 minus 17.5 over 3 minus 1. I get a change of 2.5. So I'm changing 2.5. I'm changing $2.50 for every ice cream purchased. So if I go to the next one, I purchased from 3 to 6. I purchased 3 more ice creams. So that's 17.5. 17.5 minus 2.5 times 3, because I have 3 of them. I should be at 10, and I am. And then next, we've got from 7, or from 6 to 7. Well, that should drop 2.5 again, but it doesn't. It drops 3. So which pair of values in the table is incorrect? Well, that's got to be the 0.77 is incorrect. What was the correct value? Well, it should be 7, and from 10 we should drop by 2.5. So 10 minus 2.5 leaves me with 7.5, and then we can check that one more time. I'm going to drop 2 more ice creams. So we should be at 7.5 minus 2.5 times 2, and that leaves me with $2.50. So this is my part that was wrong. Explain how you found your answer. We had a common difference, or slope, of -2.5 dollars per ice cream. All right, number 12, given the table, what is the equation for the table? Well, if I look at this, it's not linear, 2, 4, 8, 16, 32. It's definitely exponential, so it's going to be f of x equals a times b to the x. A is my starting value. My starting value always occurs when x is 0. So it's 8 times b. B is my common ratio, which it looks like times 2 times 2 times 2 times 2. So it's 8 times 2 to the x. Write the domain and the range of the function. So the domain, it's an exponential function, so it's negative infinity to infinity. My range, my graph is going to be its growth. It's going to look like that. So it has, it's going to look just like that graph right there. If we actually graph it on a calculator, we're going to get that it goes from 0 to infinity. 13, a ball is dropped from a height of 50 feet. It rebounds 2/3 of the height every time it hits the ground. Write a function that models the height of the ball over time. So f of x equals the starting height, which is 50 feet, times the ratio. Well, the ratio is that it goes back up 2/3 of the original height to the x power. There's my function. Part B, how would your function change if the ball were flat and only rebounded 1/8 of the height every time? Well, that'd be f of x equals 50 times 1/8 to the x power. 14, use the graph below for the intervals 0 to 10. So these are x values. Which function appears to be increasing the fastest? So if I'm just looking from 0 until 10, so just in this region right here, just that stuff right there, which one's increasing the fastest? All I have to do is look at my outputs. They'll start at 0, and if I follow these up, where does each one cross that line 0? So these are all increasing. This one is the highest, which is my function f, increases the fastest. Part B, for which interval from 10 to infinity, which function appears to increase fastest as x gets larger? Well, k and h definitely are still going slowest because as we get bigger, so we're looking at this part of our graph now. So k and h are never going to catch up to f and g. But right now, f is going faster because it's still above. But somewhere around right here, we can tell that this graph is going to go here, and this graph is going to start coming inside of it because it's getting taller, quicker. So eventually, g is going to start getting bigger faster. So if we go all the way to infinity, so if we go all the way as far as we can to the right on our graph, my four functions, like if I were to zoom like way out, k would look like this, h would still be doing that, g now would be like this, and f would be like that. So this is g, that's f, that's h, and k. So eventually g is going to get bigger faster. 15, use the table or graph to place the functions in order from smallest to greatest as x increases. So we could graph each of these functions. And let's go ahead and do that actually. So I'm going to go to my graph, and I'm going to go 10 to the x. I'm going to go x cubed. My next one is 16x. My next one is 2x squared. And 3 to the x. And if I look at these, and move some of this stuff out of the way, I only care about the positive side of the graph. So smallest to greatest. So the smallest graph if we keep, I'm just panning up and up and up and up and up. So we get here, and so now this is my fastest, second fastest, third fastest, fourth fastest, fifth fastest. Took me a long time to get there, but now I can look at the colors. My slowest graph is the black one, 16x squared. Then I have 16x, then I have 2x squared, then I have x cubed, then 3 to the x, then 10 to the x. So I have 16x, 2x squared, x cubed, 3 to the x, 10 to the x. And we can just graph it and see which one is going to move. Eventually, as x increases, that's the order we're going to be in. Alright, 16. Based on the change per unit, choose an appropriate type of function to model the situation. When I look at this, I notice that it's not increasing or decreasing by a constant rate. But if I divide those, we have 27,000 divided by 90,000, we get 3/10. Or if I do 8,100 divided by 27,000, I get 3/10. I have a common ratio of 3/10. That means it has to be exponential. Justification, common ratio of 3/10. 17. What is the common ratio for the following exponential function? Once again, we can just divide. Remember, we're dividing backwards. 6 divided by 1.5, or 24 divided by 6, or 96 divided by 24. That should all give us the same thing. Just 4. 24 divided by 6, we know it's 4. 6 divided by 1.5 is 4. And the justification, that's my justification. The actual division. 18. A small company has an average monthly electricity use of 8,000 kilowatt hours last year. Their 5-year plan calls for average monthly electricity use to be reduced by 10% each of the next 5 years. Identify the initial value, growth rate, growth factor, and the equation for the situation. So the initial value, we can see it, is 8,000 kilowatt hours. Now growth rate and growth factor. Growth rate is the actual percentage that we are increasing or decreasing by. So the growth rate, if we change 10% to a decimal, 0.10. The growth factor is that 1 plus r or 1 minus r. That's my growth factor. Since we are reducing, it's going to be 1 minus r. So it's 1 minus 0.10, which is 0.90. And we put those together, our equation, y equals 8,000 times 0.90 to the x power. That is my function, or my equation, for the amount of energy used. 19. Initial investment of $10,000 grows at 11% per year. What function represents the value of the investment after t years? So $10,000 is what we start with. Those all say 10,000. It grows at 11% per year. So my growth rate is 0.11. My growth factor, since it's growing, it's 1 plus r, which is 1 plus 0.11, which means it's either A, B, or that's it. Can't be C, can't be D. Because it's got to be 1 plus 0.11. Those are the only two that have that. And so the question is it a little t or a big T? Since it's exponential, it's got to be the big T. I'm sorry, the little t, because it's exponential. It's a times b to the x power. 20. The number of wolves in the wild in the northern section of Coconino County is decreasing at a rate of 5% per year. Your environmental studies class has counted 80 wolves in the area. Write a function representing the number of wolves each year. So again, f of x equals my initial value, 80, times my rate. It's decreasing, so it's 1 minus my rate, which is 0.05, to the x power. So f of x is equal to 80 times 0.95 to the x. After how many years will the population of 80 wolves drop below 15 wolves if this rate of decrease continues? Well, couple things I could do. I could just plug in numbers for x. So like for instance, I could figure out like what f of 7 is. I just pick 7 as a random number. And f of 7 gives me 80 times 0.95 to the 7th, which is still basically 56 wolves. Nowhere close to it. So I could do that a whole bunch of times till I get there. Or I'm going to use my graph. I'm going to clear the scratch pad real quick. And I'm going to plug in my function 80 times 0.95 to the x. And then I'm going to make another function which is equal to the value that I'm looking for. I'm looking for when is it going to reach 15. Press enter. Nothing happened. Nothing happened because I can't see it on my window because my window only goes up to y equals 7. To change my window, I do menu, window zoom, and I'm going to use zoom fit A right down here. And if I move it just a little bit, now I can see my line y equals 15. And if I keep sliding over and over and over, now I can see where they cross. They're going to cross right there somewhere. Menu, analyze graph, intersect, find my two intersections, and there we go. In 32.6 years, there's going to be 15 wolves left. So we're going to say between 32 and 33 years. And last couple of problems, number 21. Each year the local tennis club sponsors a tournament. Play starts with 128 participants. During each round, half the players are eliminated. What is the average rate of change between the first and third round? Well, so look right here. So the first and the third. So if it's average rate of change, we're looking for the slope of the line between those 2 points. So I have to know what is that point and what is that point. Well, this point down here is 3 something. Not sure what it is. And this point up here is 1 something. Well, we know that we started with 128 people and we're cutting it in half each time. So if we had 128 to start, after 1 round we should be down to 64. And then after 2 rounds we should be down to half of 64, which is 32. And then after 3 rounds we should be down to half of 32, which is 16, and then 8, and then 4. So what is the average rate of change between 1 and 3? Well, we're going to calculate the slope. Remember, slope is y2 minus y1 over x2 minus x1. That's going to be 16 minus 64 over 3 take away 1. That's 16 minus 64 over 3 take away 1, which gives me a slope of negative 24 players per round. So I'm averaging losing 24 players per round. Last one, for the two functions f of x equals 3x plus 4 and g of x equals 2dx minus 5, which function has the greatest rate of change over the interval 1 to 6? Justify your solution. Once again, rate of change is going to be the slope between those 2 points. So for f of x, I'm going to figure out what is f of 1 and what is f of 6, because I need to know those y values. If I plug in a 1, that's 3 times 1 plus 4, which is 7. And if I plug in a 6, that's 3 times 6 plus 4, which is 22. So m is 22 minus 7 over 6 take away 1. That's going to be 15 over 5, which is 3. So the average rate of change for f of x is 3. We're going to do the same thing, but this time for g of 1 and g of 6. So if I plug in a 1, 2 to the 1 minus 5 is negative 3. And g of 6 is 2 to the 6 minus 5. 2 to the 6 minus 5 is 59. So that change is 59 minus negative 3 over 6 minus 1. That's going to be 62 over 5. And 62 divided by 5 is 12.4. So which one has a greater rate of change? G of x has a greater rate of change. Technically, we didn't even have to do the math because we know that an exponential function will grow faster than a linear function, so we could have said that because it's exponential, it's going to grow faster over that interval from 1 to 6. That's the end of our review. Make sure you study. Good luck on the test.